Okay, hello students. Welcome to the next online lesson in real analysis. Thank you so much for your responsibility, for your hard work despite the obstacles of online platform. And today you will represent your presentations about different topics in real analysis. And let me screen share and let's start.
Yaxşı dolanmışıq, indi dolanamadık.
Okay. First is Riemann integrability. Whose is this topic?
It's my teacher. It's our.
This is Hanım
Nermin.
and Nermin. Okay, let's start Hanım and Nermin.
Okay, so teacher, Nermin and me are going to present the Riemann integrability in real analysis. So firstly, could you, firstly, I'm gonna tell you the some definitions about the Riemann integrability, and which is represent the first formula on the first slide. And the Riemann integrability, a function f closed set AB is said to be Riemann integrability on closed set AB if there exists a number L included R such that for every epsilon is greater than 0, there exists sigma greater than 0 such that if P is any tagged partition of closed set AB. So this is the formula of this definition, first definition, which is in the model is Fp minus L less than epsilon. So we denote the Riemann integrability function on closed set AB with the R closed set AB. And the last formula of the first slide, which is L is equal to integral A from B F. And instead of L, we always write the Riemann integrability of F over closed set AB. And the next slide is for the Nermin, please.
Great. And Nermin, Aliyeva or Maharramli?
Maharramli.
Please, Nermin.
Yes, now we have theorem. If G is Riemann integrable on AB and if Fx is equal to Gx except for a finite number of points in AB, then F is Riemann integrable and integral of F over AB is equal to integral of G over AB. Okay, let's see. Be a point in the, okay.
You don't need to prove the theorem, okay? Yes.
Okay.
So
Okay.
continue, please.
Yeah, it's the proof.
Uh-huh.
So you can turn the page, the last one.
Then next theorem.
Nermin, if you wanna, you can.
Yeah, okay. Teacher, I can't see.
Suppose that F and
It doesn't seem that in our presentation.
Yeah. You present.
Me? Okay. We have a theorem which is the suppose that F and G are in the R, which is closed set, and if K is included R, then the function Kf we will write in Riemann integrability, like we will write the K in front of the integral K integral A from B
as coefficient, yes?
Yeah, as like this, and the next one is in the B. If you want to write the sum of the F plus G, we will separately write it in integral, which is integral AB F plus integral AB G. And the last one is if Fx is less than Gx, so we will write it in the Riemann integrable to like integral ABF less than and equal integral ABG.
Thank you.
Great, thank you. You are my diligent students.
Thank you.
There is no unclear part in your presentation. You really give a brief but detailed information. Yes, please.
Mən bayaq soyan mamam idi, nədadır da, mən gətirib o qədər ağlayıb ki, mamam bütün nəslimi soydu.
You are in the recording, I said. Okay, don't worry. I said, say hi. Okay, let's continue. Thank you for Nermin and Hanım. Who is next? Asli is not here yet. Güler and Nermin Aliyeva, are you here?
Yes, we are here.
Great. Okay, let's continue with you.
Okay.
Uh-huh.
Who will start? You or me?
Limit theorems.
You. Yes. Okay, today our topic is limit theorems. And today we will have brief information about limit and some theorems. And now, and you can see this is our agenda of today. We will talk about definition of limit, we will talk about properties, we will talk about limits of polynomials and its proof and squeeze theorem. It is a popular theorem. Okay, now I will talk about definition of limit. Okay, what is limit? We are talking about limit and we don't know what is limit. In math, limit is value that function approach as the input approach some value. And how can we say that? Imagine that there is one function and it is approaching always some value. This is limit in basic way. And for example, we have a given function f and its limit L, and approaching value is C. And there is always one epsilon greater than 0. There is one sigma greater than 0, such that always x. Then we will get x minus c, or modulo of x minus c lesser than sigma and greater than 0. Then we will get f minus l less than epsilon. This is limit definition of limit, we can say.
Okay.
Then actually we have a theorem.
We have a theorem that if A is subset of A and if A is equal to R, there is a limit if it's bounded on some neighborhood of C, and there is a small graphs of it that where is X come from, how to is approaching L at the same time epsilon. Actually, we also passed it a little bit in the previous course, and there is some properties about limit. And that there are some famous properties that we always use it in our lessons, and a small theorem that let A is subset of R and f and g be functions on A to R, and let's see included to R be a cluster point of A. The cluster point is the point where all points gathering in one point, let's say, and further the let be included R. Here I just small mention as a I let's say showed X approaching C as a triangle. The A variant, the limit X approaching C, f is equal to L and G is equal to M. If limit X approaching C, f plus G is equal to M, L plus M, f minus G is equal to L minus M. If multiplication of G is equal to L multiplication of M, and at the last one B multiple of F is equal to B multiple of L, and B here is a constant. And the B variant, A approaching R, there is hx isn't equal to 0 for all x included A, and limit x approaching C, then h isn't equal to 0, then limit x approaching to C, f divided by h is equal to L divided by h.
Great.
And here is some examples, some let's say isn't brief examples about it. And in the next page, you can see the solutions of it. It's based on properties about division or multiplication, how is the process is going on. And in the
next slide, I will talk.
yes.
Okay, in the next slide, we'll talk about limits of polynomials. And actually here we have a proof, and I will talk about it. Limit of polynomials, for example, we have a limit x approach c, and we have a polynomial px. Px, we will get pc. And how? In the proof, you can see that we have a limit x approaches c and px, and px, p of x is equal to an x of n x plus an minus b an minus 1 x of n minus 1 and blah blah blah. It's going. And according to our properties, if we divide if we separate each part of limit, we will get third line, third row, you can see. And then if you put c to x, we will get an c top n, an minus 1, c top n minus 1. And then it will give us p of c. And we proved already our polynomials. And like that, in the second statement, you can see also division of the polynomials.
Okay, great. And theorem, but you don't need to prove the theorems, okay?
Okay, sorry. And then Gül,
okay, then we will just read briefly about theorems. First one is if a subset of R, there is a that C is equal to R, be a cluster point of A. If fx, the function fx is between A and B for all x, and x is different from C, there is a limit that limit x is approaching to C is between A of B. And from here, there is a theorem, Sequoia's theorem, famous theorem, that for a limit version of the same function, if a subset of R for every fg hash, there is a that approaching to R goes to R, let's say, there is a cluster point of A if gx is between fx and hx for all A. Their limit f is equal to L, and a limit f is equal to h, and also limit is equal to g. That all of them is equal to one limit L.
Great.
Some example, and that's all.
Great. Thank you, girls. You did great work despite the online platform, the online lessons, the limit of your internet connection, but you really did a great job. Thank you for your effort. And let's continue. Who is next?
Muallim,
Yes, Ertuğrul, do you want to present?
Ben istəyirəm ama uşaqlar qrupda
in
yazıblar
English,
ki.
please.
Tamam. In group chat, in our Zoom chat, some girl write, please, we speak next. If you want, you see who.
Okay. Let me.
After them, I speak.
Okay. Who wants next? Who wants?
Ayşegül istəyirdi müəllim.
Ayşe?
Yes.
Ayşe.
Ayşe. Let me see the presentation of Ayşe is here. Ayşe and who?
Ferman.
Pervane and Ayşe. Okay. Please, girls, let's start the mean value theorem.
Hello, teacher. Talking about the Rolls theorem. Please, screen is
Start.
Suppose fx is a function that satisfies all the following. Fx is continuous on the closed interval a and b. The second is differentiable on the open interval a and b. And the last one, if a is equal to fb, then there is a c is placed between a and b. And if derivative c is equal to 0. Let's example determine all the number c which satisfy the conclusion of the Rolle's theorem for fx is to x over 2 minus 2e 8 on -1 and 3 closed interval. Solution is that the function is a polynomial which is continuous and differentiable everywhere. First, the function is continuous on closed interval -1 and 0, -1 and 3, and differentiable and open interval -1 and the second, if -1 is equal to f3 and is equal to -5. If derivative x is equal to 2e minus 2, and then solve the if derivative c is equals 0. We found a single value and it's in the interval, so the value we want is c is equal to 1. And Ayşe?
Okay, now I wanted to speak about the mean value theorem. Suppose fx is a function that satisfies both of the following. First, fx is continuous on the closed interval a and b. The second, if fx is differentiable on the open interval a and b. Then there is a number such that a and c they're located between A and B. Also, the C can be parallel on the x-axis, and then we get that this formula f derivative C equal to fb minus fa divided b and b minus a. Then if you look the example, we are clearly understand. For example, determine all the number of C which satisfy the conclusion of the mean value theorem for this formula on 2 and 5 interval. And we know that our first law, the function can be continuous, other synchrotron differentiable, and we see that our function is continuous on the closed 2 and 5 interval and differentiable on open 2 and 5 interval. If we solve this for this example, we get that C we find two values, but we take the second answer because our answer located 2 and 5 interval. At the end, we find our answer C equal to 2.6.
Okay.
Patty.
Theorem, let if I is approached to R, differentiable on the interval I, then if it's increasing on I, if and only if derivative x is bigger than 0 for all x is entered I, if is on I, if and only if derivative x is less than 0 for all x entered I. Example, if x is equal to
okay,
Ayşe.
You don't need to explain the example. I think it's clearly represented in your presentation. So thank you, girls. You are my tireless girls. Thank you for your effort. And but I think it was the turn of Ertuğrul, no?
No,
in English, please. In English. Ertuğrul, do you let Allah verdi or
Allah verdi, eğer tez olarsa olar. Çünkü bende çok uzundu.
Thank you
Eğer
very
mən
much.
oldu.
okay,
Mən də
Allah verdi. Allah
Bir də
verdi.
mən ona kimi mənim
Əgər Ertuğrul
slaydım
da
yükləsəz
puldusa
olar.
qısalar eləsin, sonra Ertuğrul eləsin də, please.
Yes, yes.
Məncə
Okay.
Ertuğrul ən axıra qalsın.
But
Müəllim,
Ertuğrul has just 2 or 3 minutes to explain, to represent his presentation. Okay, we have our time limit. Our
Yaxşı,
time is
müəllim.
limited. Okay.
Müəllim, ola bilərmi ki, mənimkini bir yükləsəz? Çünki mənimki yüklü
Okay.
olsa daha yaxşı.
mən qumral eləmişəm ha.
Okay.
Müəllim, kim danışacaq
Çünki
indi?
yəni
Mən
online
danışıram.
olaraq açsaq,
Is Allah verdi. Next is Allah verdi. Yes.
Bəli.
Okay.
Allah verdi danışmaq istəyirsən.
Niyə danışmasın?
In English,
Müəllim.
please. In English.
müəllim, ona kimi mənim o şeyi yükləsəz olar.
Okay, Allah, Ertuğrul, okay. Allah verdi. You were with Gumral, yes? But
Yes.
Gumral is not here.
Müəllimə.
You will
Actually,
represent it. Okay, Allah
Hospitals
verdi.
rule.
Next is you. Please continue.
L'hôpital.
L'hôpital's rules. We create my partner Kumral Mustafa.
Uh-huh.
In mathematics more. Azərbaycanca danışım
No
xahiş
in
edirəm.
English, no in English. In mathematics.
In mathematics, for more especially calculus, hospitals rules or L hospitals rules provides a technique to evaluate limits of indeterminate forms. Application of the rule often converts an indeterminate form to an expression that can then be easily evaluated by substitution. The rule is named after 17th century French mathematician Julien de L'Hopital. Also, the rule is often attributed to L. Hospital. The theorem was first introduced to him in 1694 by the Swiss mathematician John Bernoulli. L. Hospital's rules can help us calculate a limit that may otherwise be hard or impossible.
Okay.
Uh-huh.
And this is the derivative.
Yes, it says that the limit when we divide one function by another is the same after we take the derivative of its function. In symbols, we can write a limit x
approach to c.
X approach to c fx divided jx equal limit x approach c f derivative
f prime x.
F prime x divide j prime x.
And next, this is the example, yes, you talk about, but you don't need to explain the example. I think it's clear. And next slide. L'Hopital's rule.
L'Hopital rule'su nə üçün istifadə edirlər mənim? Yəni
in English states that. Do you see the screen? Can you see the screen?
Yes.
Please read from the screen.
Okay. L. Hospital's rule states that for function f and g which are differentiable on an open interval, I expect possible at a point c contained in A. If limit z approach to c fx equal limit z approach c gx equal 0 or minus plus minus
negative positive
positive infinity g
prime x
with x not equal 0 for all x in a with x not equal c and limit f
fx over g
f
when
over
approach
fx
c.
divided g
Is equal to limit x
is
approach
equal.
c.
Yes, the differentiations of the numerator and denominator often simplifies the quotient or converts it to a limit can be evaluated directly.
Okay, and this is the general form. And
Nazan'ın sifətinə baxdım.
really,
Ağzım
indeterminate.
turşudu.
There is in indeterminate form the theorem, the Cauchy mean value theorem. Please read the theorem and the Cauchy mean value theorem, and then we will finish.
Okay. Let f and z be continuous on a and b interval and differentiable on a and b, and assume that g is a theorem not equal 0 for all x in a b. Then there exists c in a b such that fb minus fa divided gb minus ga equal f theorem as f prime c divided g prime c.
Thank you, Allah Verdi, for your
Thank you very much.
Hard work. Really, you are my dear student.
Thank you very much.
Herhangi bir ders atacaksın.
Good luck mənim, hamınıza uğurlar. Olar mən gedim mənim.
Yes, of course. So, friends, let's continue with Şeyda. Şeyda. And who?
Nazan.
Şeyda and Nazan. Where is your presentation? Let me find. Nazan is here. The algebra of sets. Please, Şeyda.
Our topic is the algebra of sets. What's a set? If A denotes a set and X element of A, we will write X is element of A. If X does not belong to A, we will write like this. If A and B are sets, such that X is element of A and X is element of B, A is contained in B, or A is a subset of B. If A is a subset of B and there exists an element in B that is not in A is a proper set of B. Definition: two sets A and B are equal if they contain the same elements. If A and B are equal, we will write A equal to B. Next one, set operations. If A and B are sets, then their intersection denoted by like this is the set of elements belong to both A and B. The union set, the union of A and B denoted by A union B is a set of all elements that belong to either A or B. We have example, if set A is equal to 1, 2, 3, 4, A and F, B is equal to
Şeyda, you don't need to explain the example. I think it's clear to everybody, okay? Let's continue with set operations definition.
The set, empty set, if the set has no element, is called the empty or the void set. If A and B are sets with no common element, then we say that A and B are disjoint or non-intersecting sets.
Great.
Okay, this is my part. I gonna talk about theorem. Let's ABC be in a set, then A intersect A equal to A and A union A equal to A. It's called in idempotent relationship. A intersect B equal to B intersect A, and vice versa. It's called commutative relationship. C bracket A intersect B and intersect C equal to A intersect B intersect C. Also union of all this, so called associative relationship. D A intersect bracket B union C equal to A intersect B union bracket A intersect C, called distributive relationship. Next, definition of complement. If A and B are sets, then complement of B relative to A is the set of all elements O
A that do not belong to B. Something went wrong with Nazan's internet connection. And there is the final theorem. I think this is the end. Yes? Sheyda, do you want to continue?
Yes, teacher. Definition. If A and B are two non-word sets, the Cartesian product A and B is a set of all ordered pairs A, B with A element of A and B element of set B.
Great, thank you, girls. Great. You are so tireless, really. Thank you. And let's continue with who? Who is the next?
Asli and Könül.
Asli and Könül. Where is Könül and Asli? Let me find. Here. Lebek measure.
Belki sırayla geliyor. Böyle çok karışık
But they have no time. Their lesson will start. Let's continue with them, and then we will continue in order. So the Lebek measure. Könül and Asli, please.
Yes. Today our topic will be Lebesgue measure. What is the Lebesgue measure? We know that the length of a bounded interval I with endpoints A and B where is a less than B is defined the length of A is equal to B minus A. Or if I is a positive infinity, the concept of length or measure to arbitrary subset of R. When one attempts to do this, one is less reasonably, but has become not forced people to carry this out in complete detail and to apply it with great success to many problems of real and complex analysis, especially to the series of Fourier series integrals. The Lebesgue measure is an extension of
please speak louder. We can't hear you, please.
Okay. The Lebesgue measure is an extension of the classical notation of length and area to more complicated sets. Now let's learn some properties. Given a set A of real numbers, mu of A, which is the Lebesgue measure of A, will donate its Lebesgue measure if it is defined. For every interval I, mu of I is equal to length of I, which means Lebesgue measure of I is equal to length of I. Second, if A is a subset of A, then A is a less than or greater than mu of B is less than to or each point X is included R. We define A plus X0 plus of A union B is equal to mu of A plus mu of B. Second definition 1, 2, 1, it's as this part.
Yes, let's learn some definitions. Definition 1, 1. A subset A
which is a subset of R, is called Lebesgue measurable if for every subset E of R is mu E is equal to mu E and R intersection plus mu E and a complementary intersection. The next definition is if E is a Lebesgue measurable set, then the Lebesgue measurable of E is defined to be its outer measure mu I and is written mu I. Theorem 1-1. This is Q&A's part. Yes.
Yes. Let's look some theorems about Lebesgue measure. If the collection M of Lebesgue measurable sets has the following properties, both F empty sets and R are measurable, mu of empty set is equal to 0 and mu of R is equal to infinity. If mu of A is equal to 0, then which means A is measurable. If this is the A1 and A2 are measurable, which means then the union of A1 and A2, also the intersection of A1 and A2 are measurable. If A is measurable, then A plus x0 is also measurable. If every interval is measurable and mu of A is equal to outer measure of Lebesgue measure and the length of E is equal to one another. And the theorem. Yeah.
Okay, if E1, E2, and so on is a disjoint collection of Lebesgue measurable sets, then their union and the union of these sets with intersection with A is equal to each of them intersects with A, mu is mu A intersection of E1 plus mu A intersection of E2, and so on. Proof. Let's use the measurable.
Ashley, you don't need to prove this theorem, and I think really you did a great work. Your presentation is very long and detailed, I think, but unfortunately we have less time. So you talked about Lebesgue style dress measures and also theorems about the examples. Great work, girls.
We provided all the types of Lebesgue measurable sets in our slides.
Great, really good job. Thank you for your effort. Thank you, girls. It's enough, I think. It's clearly, you clearly represented your presentation, and you got the highest degree also. Thank you, girls.
Thank you, teacher.
Let's continue with, Aysel, you did your presentation.
Buradayım ben.
Okay, Aysel and Solmaz, let's start.
Sesin çıkmasın. Okay. Our topic is derivative, and in this section we will present some of elementary properties of the derivative. And let us start from the definition 1. Let E included R be an interval. Let F is E approach R, and let C included E. We say that the real number L is the derivative of F at C. And our formula is like that, f of x minus f of c divided by x minus c and minus L in model is less than epsilon. And in this case, we say that f is differentiable at c, and we write derivative f of c for L. In other words, we can write the formula like this. Derivative f of c.
I think it's enough for you. Thank you for your hard work, really, despite the big... Kiss her, please. Thank you. You got the greatest degree also. Thank you. Let's continue with Solmaz. She's hungry. Feed her. Okay, Solmaz.
Okay, I'll continue.
Solmaz,
Can
let's
you please?
continue with this theorem,
Yes.
6.1.2.
Yes, okay. If f and I approach to r has a derivative at c included I, then f is continuous at c. So should I tell the proof or
no, you don't need.
takes a long time?
The next theorem.
Yes. So the next theorem is I included r and be an interval. Then let's see included I. And let f I approaches R and g I approaches R be functions that are differentiable at C. Then there are some properties for it. If alpha approaches R, then the functions alpha f is differentiable at C. And alpha f, the derivative C, equal to alpha f derivative C. B, the function f plus g is differentiable at C, and f plus g derivative C equal to f derivative C plus g derivative C. Then we have a product and quotient rule. Product rule is that the function fg is differentiable at C, and fg derivative C equal to f derivative C g C plus fc multiple g derivative. Then quotient rule, if gc not equal to 0, then the function f divide g is differentiable at c. Yes, and you can see in the slides the equation.
You don't need to mention the corollary and
yeah, there are some theorems like a chain rule and also cathedral theorem if you go down.
And this is the differentiate and simplify of fx. Yes,
yes, there are some examples.
Let's continue with this theorem.
Yes, Theodore's theorem. Let f be defined on an interval I containing the point C. Then f is differentiable at C if and only if there exists a function w and I that is continuous at C and satisfies. About the equation fx minus fc equal to phi x multiple with x minus c for x included I. In this case, we have pc equals to f derivative c.
I think it's enough, Solmaz. Thank you girls for your hard work. Thank you, really. You also got the greatest degree, as I said, and your other friends. And let's continue with Asli Hanım Güler. Kazım, who is you?
Lale and Aliye.
Lale and Aliye. Okay. Mathematical induction, really interesting topic. Let's start.
Yes, teacher. Benim sesim gelir.
Yes, please.
Okay, we will talk about mathematical induction. Mathematical induction is a special way of proving things. And we talk about its definition, history, and how it reflects on our natural life. Okay, what is definition? Mathematical induction is a method used to establish the validity of statements that are given in terms of the natural numbers. Mathematical induction is a mathematical proof technique. It is essential used to prove that a statement Pn holds for every natural numbers n equals 0, 1, 2, 3, and so on. That is, the overall statement is a sequence of infinitely many cases, P0, P1, P2, P3, and so on. Informal metaphors help to explain this technique, such as falling dominoes or climb a ladder. Okay, Alia will give very brief information about its history. Okay, Alia.
Okay,
Let's
history of mathematical.
Alia. Hi, Alia.
Yes.
Alia,
Hi.
let's continue with, not with history, let's continue with some properties.
Okay,
Mathematical
okay.
induction proves that we can climb the basis. Let me please. Principle of mathematical induction.
Principle of mathematical induction. For example, we have a subset and n is the subset of S. We have two rules. Firstly, one must be include the S set is given. Secondly, if k include S, then k plus 1 also include S set, then S is equal to n. N is a subset of S.
And here is the proof.
Okay, a proof by induction consists of two cases. The first, the base case, proves the statement for n equals 0 without assuming any knowledge of other cases. The second case, the induction step, proves that if the statement holds for any given case n equal k, then it must also hold for the next case n equal k plus 1. These two steps establish that the statement holds for every natural numbers n. The base case does not necessarily begin with n equals 0, but often with n equal 1 and possibly with any fixed natural numbers, n equal natural numbers, establishing the truth of the statement for all natural numbers n bigger or equal natural numbers. Okay, next example.
Let us look at the example. Example we must prove by with mathematical induction. 1 plus 5 plus blah blah plus 2 times n minus b is equal to n square. N in here include the natural numbers. Firstly, I said previous slide, we must look at the first in n equal. When we put in 1 instead of, we get 1 equal to 1 square is true. Second step, we must look at in equal to k. We write k instead of the n, and we get 1 plus 3 plus 5 plus 2 times k minus 1 equal to k square is true. Then we must k plus 1, and we get 1 plus 3 plus 5 2 times k minus 1 plus 2 times k plus 1 minus 1 and k plus equal to k1 square. And we saw that in above 1 plus 3 plus 5 2 times k minus 1 equal to k quadrate. We wrote in second equation, and we get k squared 2 times plus 2 minus 1 and equal to k squared plus 2 times k plus 1, and this equation is true and proof is complete.
Great, thank you, girls. You don't need to prove another example. Thank you for your effort also. You did great work.
Welcome.
And let's continue with Ertuğrul. Ertuğrul is waiting us. Are you
Müəllim,
here,
ola bilərmi
Ertuğrul?
ki, mən buradayım. Ola bilərmi ki, mən gələn dəfə soruşum, məndən öncə Arzu ilə Nəzrin var, onsuz onlar eləmək istəyirdi, nədən adı. Çünki mənim işim biraz uzundur. Yəni reallığı danışaq da.
Okay. Okay,
Arzu ilə Nəzrin buradadırsa.
Nəzrin, are you here?
Yes.
Please.
Ertuğrul, thank you, by the way.
Okay.
So today we're going to talk about completeness property. I think these things. Can you download the presentation, please? or I can also share if it's possible.
Why you want to?
Yani
can't
download edeceğiniz daha yaxşı. Ha, belə, okay.
Okay.
So we will talk about completeness property with Nazrin. Nazrin, if you want, you can start.
Okay, what's completeness property about? The completeness property of the real numbers. The completeness property is also often called the least upper bound property. The completeness property above is a crucial axiom. A similar theorem regarding non-empty subsets S of the real numbers that are bounded below exists and is proven below. Theorem 1, every non-empty subset S of the real numbers that is bounded below has an infimum in R.
So I will continue with
next slide.
definition. Yes, definition 1. So here, let S be a non-empty subset of R. So here we have some properties about it. A1, the set S is said to be bounded above if there exists a number U belongs R such that S less than and equal U. For all S belongs to big S, each such number U is called an upper bound of S. Actually, we talked about it in our previous lessons. So the set S is said to be bounded below if there exists a number W which belongs to R such that W less than and equal to S. For all S belongs to S, each such number W is called the lower bound of S. So at the end, a set is said to be bounded if it's both bounded above and bounded below. A set is said to be unbounded if it's not bounded, actually. Let us continue with other definition.
Definition 2. Definition, let S be a non-empty subset of R. If S is bounded above, then a number is said to be a supremum or a least upper bound of S if it satisfies the conditions. U is an upper bound of S, and if V is an upper bound of S, then U will less than equal V. If S is bounded below, then a number W is said to be an infimum or a greatest lower bound of S if it satisfies the conditions. W is a lower bound of S, and if T is in a lower bound of S, then T less than and equal W.
So let's continue with our lemma as a result of our completeness property. So lemma is said that we have two results. S is less than and equal U for all S belongs to S. And if V less than U, then there exists S which belongs to S such that V less than S. At the end, we have an example. Nazrin, do you want?
Example, yes.
Yes.
But you don't need to explain the example. Here you find out the supremum and infimum, yes? And you find out that supremum is 2 and
1 actually.
Numbers such as 2 and 3/2 are upper bounds, but the supremum should be 1. Okay, great. Girls, thank you, my diligent girls, my dedicated girls. Thank you so much for your effort also. You also get a highest degree. And let's continue with food. Leila, are you here?
Yes.
Khatra and Leila. Let's continue with you. Limits of functions. Okay, please start.
In this section, we will talk about limit.
Please speak louder. We can't hear you.
In mathematics, A limit is the value that a function or sequence approach as input approach some value. The concept of limit sequences is further generalized to concept of limit of a topology net and is closely related to limit and direct limit category theory. A limit is denoted like that. Aşağıda.
Sorry. Which slide? This?
Yes. We will introduce the important notion of the limit of a function. An intuitive idea of a function if having a limit L at the point S is the values of fx are close to L when x is close to S. What is necessary to epsilon sigma definition?
Where is your? I can't find the slide. This?
Yes, it's next.
Next. Theorem? This theorem?
Yes.
Okay.
Theorem, a number C is from R is a cluster point of the subset of A of R if and only if there exists a sequence AN in A such that the limit of AN is equal to C and AN is not equal to S for all natural numbers. Okay. It's proof of.
You don't need to prove. Here is the examples. Yes.
For example, for the interval A1, 0, 1, every point of the closed interval is a cluster point of A1. A infinite set has no cluster point. A infinite set N has no cluster points. And D1, the set A4 is equal to 1 over n from natural numbers has only point 0 as a cluster point, and if E is from set 0 to 1, then the set A4 E intersection with Q consists of all rational numbers in E. It follows the density theorem. Hatırı, please.
Hatırı.
Yes, I talk about definition of the limit. Let A be from R.
Hatırı, we cannot hear you. Could you please speak louder, talk louder?
Let A be from R and let C be a cluster point of A for a function if A R, a real number L, is said to be a limit of at C. Given any epsilon greater than 0, there exists sigma greater than 0 such that if x be from A and 0 greater than modulo of x minus C and less than sigma, then if modulo of fx minus L less than epsilon. This is definition of limit. And L equal to limit x approach C fx, or L equal to limit x approach C f. Next slide. There is a theorem. If A R and if C is a cluster point of A, then F can have only one limit at C. This is proof.
You don't need to prove the theorem, and also theorem about the cluster point. Let's continue with sequential criterion for limits.
Sequential
Theorem.
Yes.
Leila.
Leila, please.
Sequential creation for limits. Let f be a function a from a to r, and c is a cluster point of the a. Then following are equivalent. First is limit x from c, x to c is equal to x approach to c is f equal to L. For every sequence xn in A, that converts to A such that xn not equal to c for all natural numbers. The sequence xn converts to L. And here's proof.
You don't need to prove, and you also mentioned the divergence criteria, limit theorems also, but your presentation is really very big, and we have very less time, so we cannot read all the presentation, but you really give the detailed information. I think it's clear to everybody who heard you. Thank you, girls, for your effort, also for your hard work. You are my tireless girls. Thank you. And you also got the greatest degree. And let's continue with who?
Ömer Tuğrul'dan sonraki azımdan ben verebilirim.
Okay. So let's continue our representation. And today is Ertuğrul's turn. Let me open the presentation and share the screen. Okay. Ertuğrul, I've downloaded your presentation. Where is this?
Birden bir sayımız azaldı ya.
Kameranı da açsa Ertuğrul.
Okay.
Kameranı da açın.
Yes, please.
Kameranı niye açın? Kamera beni açın.
Camera.
Gel. Biraz düzenleyeyim. Böyle bezeneyim falan filan. Tamam. Power of continuum. Today we talking our lesson is power of continuum. What's the power of continuum? Please next slide.
Okay.
Bir dəfə basın, mən bəsdir, bir dəfə.
Okay.
Power of continuum in the mathematical field of set theory, the continuum means the real numbers correspond real number. Yani we say the continuum is a real number or corresponding cardinality infinite cardinality number. George Cantor proved that the cardinality is larger than infinity, namely Aleph null. He also proved that C equals two superscript of Aleph null. Aleph null. Yes.
Okay.
This letter Aleph, and yes, namely where I thought this letter is Aleph. We say Aleph near the Aleph null, near the speak where is an Aleph null. Yes.
Okay.
Next slide. a linear continuum, in my opinion, linear continuum is the we talk about how we could talk about accordingly linearly. Yeah, what I say.
You can read from your presentation, Turul. You don't need to talk yourself. Okay, you can read. Just
yes,
relax.
Yes. Linear continuum is something. This continuum is according to four axioms. Firstly, C is a simple order respect to little than. If A and B is cut off C, then either A has last element or B has first element. And another slide, there is exist non-empty countable subset C of S or C such that X and Y
from
included C from C such that X Y bigger than X. Then there exists Z included S such that X greater than Z greater than Y. Separability, this is separability axiom. Another axiom is this is characteristic of real number line. If, for example, like one line, we use simple single line. First line is a linear continuum. For example, when we say the real number is linear continuum, but another real subscribed to, for example, real multiplied by real set, it is not linear. Cardinality of continuum when we the size of real number. That's all. Yani, after next slide, I explained what's the cardinality of real number, what we write them, C or denoted by C, or this letter is not like C, but graph C, graph alfabeti var, onun C'si yani normal C değil. Or modulo of R. Next slide, I prove the symbolically the C equals 2 power to aleph null. After next slide, I explain what's the aleph null. 10th slide, I explain what's the aleph null, what's the aleph 1. Aleph 1 is second smallest cardinal infinite number, cardinal number.
You don't need to prove. You don't need to prove. Please, just keep going.
I explained the next slide. No, next slide. Change the next slide. Yes, I explain what's the aleph null, what's the aleph 1, and I continuum hypothesis. What's our continuum hypothesis? What's the CFC?
Trust or falsity of this hypothesis.
Yes.
Great.
Yes. Next slide. What's the uncountability? When aleph null is less than C, it is an uncountable set. For example, R is equals or bigger than C, it is countable, but it is never şart ödemirse yani bu uncountable. Yes, not satisfied with condition. It is uncountable set. Next slide.
And the continuum hypothesis.
Yes, I explained that. Next slide. What's the continuum hypothesis? And next slide, cardinal set of integers, same cardinal. No, another slide.
The continuum hypothesis you talked about, and the cardinal of the set of integer is the same as the cardinal of the power set of integers.
Next slide, there is this infinite tree bijective with set n. I explain it one by one.
Explanation.
Yes. Next slide. The continuity of this explanation, and I explain. Ben orada figür 1, figür 2 vurgulamışam. Diğer slaytda isə figür 1, figür 2 necədir? Necə deyil.
Figure shows the infinite tree where each node gives rise to 10 branches, yes? And the second figure shows the infinite tree representing the set n. Great. Arturo, these are very interesting materials, information. We don't study this topic, but you really found very detailed information. And I think while reading this information, there is no unclear part to us. Really,
27 slide var. Tamam, 27 slide.
Yes, really, you did great work. Thank you so much.
Ama onları tək izah eləsəm müəllim, yəni belə qına dedim. Yəni bayağı zaman olacaq. Ona görə dedim ki,
yes, we have a very limited time, so let's continue with your friends. And thank you so much for your hard work, really, for your effort. You are very tireless student. Thank you, Arturo. You also got the greatest degree. And let's continue with who?
Cama. Kazım Tuncay. Müəllim. Siz danışdınız.
Tuncay gil olacaqdı, sonra da bizdə. Bayaq elə dedik.
Heç nə.
Saçımı kim yolub? Saçımı kim yolub?
Please, Arturo. Who is next? Tuncay and Kazım. Let me open the presentation.
Mən öz hissəmi danışacağım. Kazım girə bilsə öz hissəsini danışar, girə bilməsə.
Okay, no problem. You start, then Kazım will continue if he can join. Sequence and their limit. Please start.
Sequence and their limit. To find the missing number, first find rule behind the rule behind the sequence. Sometimes we can just look at the number and see a pattern. Example 1, 4, 9, 16. Answer. They are sequence. 1'in kvadratı bərabər 1, 2'nin kvadratı bərabər 4.
They are squares. In English, please.
In English kvadrat nədir müəllim, mən bilmirəm.
Square.
Square.
1 square equal to 1, 2 square equal to 4, 3 square equal to 9 və başqa.
Okay, and etc.
Xn bərabər n square. Sequence 1, 4, 9, 16, 25 və başqaları.
And etc.
A sequence is the set of things, usual numbers that are in order. Each number in the sequence is called a theorem, or sometimes element or member. Sequence 1 first theorem, second 4 second theorem, 9 third theorem və goes forever, yəni davam edir bu formada. Example 3, 5, 8 və başqaları 21 filan. After
where is your sequence. I couldn't find.
Müəllim yuxarı qalxın, çox aşağıdasınız siz.
Which part is you talking about?
Həm qalxın deyəcəm sizə.
Yes, I found.
Hə, buradayım mən, yuxarıdakında.
Fibonacci sequence.
After 3 and 5, all the rest are the sum of the two numbers before. That is 3 plus 5 equal to 8. 5 plus 8 equal to 13, which is part of the Fibonacci sequence. Rule xn beraber xn minus 1 plus xn minus 2. Now, what does xn minus 1 means? It means the previous term and previous term number n minus 1 is 1 less than term number n. And xn minus 2 means the term before that 1. Let's try the rule for the term, for the 16th term. 6 term, 6. şeyden. X6 beraber equal to x6 minus 1 plus x6 minus 2. x6 equal x5 plus x4. So that term x6 equals term 5 plus term 4. We already know the term 5 is 21 and term 4 is 13. So x
13
21 and plus 13 is 35. Ben burada bitirmemiştim. Buradan oynatın.
And you also talked about infinite or finite series. Yes, when the sequence goes on forever, it's called an infinite sequence. This is the part of chasms. Yes.
Yes, chasms.
Here are the examples. Unfortunately, Chasm's internet connection went wrong. Let me continue. Arithmetic sequences, you talked about triangle numbers. The triangle number sequence is generated from a pattern of dots which form a triangle. Great, you gave example and you talked about square number, cube numbers, and Tuncay, please read the sequence and their limit, and then we finish your presentation.
Tamam, bir tane oran tapamam.
Look at the screen. This is on my screen. Sequence and limit.
Ha, gördüm. A sequence xn has a limit p provided that for any tolerance s
greater than
0. We can obtain a real number k such that xn minus p less than s whenever the index n greater than k. Limit yakınlaşılmışsa
n
sonsuzluğu.
Approach to infinity.
Limit n approach to infinity. 2 n plus 1 equal to
plus 1
equal to 0.
Yes.
The limit of a sequence n is the number L such that if for each epsilon greater than 0, then exists an integer n such that an minus L less than epsilon. For all n greater than n, an minus L çitiştir, yani less
epsilon
means the values of an such that L minus epsilon less than an less than L plus epsilon. Each sequence's limit fall under only one of the 4 possible cases.
And great. There are the 4 possible cases, and you don't need to read them. Thank you, Kazım and Tuncay. Thank you for your effort You are also my dedicated students. Great. Let's continue with Chinara, yes?
Yes.
Chinara and Jamal.
Wait.
You are not the same. Okay, functions. Chinara and Jamal, please start.
Okay. First of all, I will start to talk. Today's topic is functions. Firstly, what is function? Function is a relation in which each element in the domain is paired with exactly one element of the range. Here in the picture, you can see just there is only one x and the function, and then the result is only one output y. Now let's change the other slide, please. Yeah, there is some rules about this. A rule if that assigns to each number of non-empty set D a unique number of a set Y. That means it's a function. It's a function from D to Y. For example, if the Y is equal to fx function is given, here's a set D is a domain of f and denoted by df. The members of y are the possible values of f. So we can say that in that possible there's a y there its range, and
no problem. Keep going.
Okay, then the set of values attained by f is a range of f. And a real valued functions of a real variable is a function whose domain and range are both subsets of the reals. This is important point too. Also, we are concerned only with real valued functions of a real variable. In this section, our definitions are not restricted to this situation. Here is some special below. There is a special kind of relations. Actually, it's about also imagination of the functions, image of them, and about the non-empty, which are the most important. Here's a say element x is the colored. Look at the here. There is say that we write a function as a y is equal to fx, and here's the x is colored the pre-image of y, and this function is from a to b. A and b should be non-empty. These are just rules for them, and we have a little note there. Just two or more elements of A may have the same image in B, and fx from to y means that on the function of f from A to B, an element x of A has image y in B, and it's necessary that every f image is in B, but there may be some elements in B which are not f images of an element of A. This just some points they above. Look at the here, for example, what actually functions look like. It's like input file is given and transformation function gives us output table, and there is also possible restrictions and extensions of functions. What is restriction? The function f1 as defined above is called the restriction of f. Here's given. Of f to d1. It's called restriction because it is defined on a smaller set. On the smaller set, the two functions agree. In other words, f1 is the same as f restricted to d1. And about the extension, here is the given. Instead of restriction, the definitions of function to a smaller set. We can also do opposite. We can extend it. Sometimes it is useful to extend the definition of function to a larger set. For example, can we do it below, please? Let G be a function with domain, and let D be a set containing. We can define a new function G2 with domain D2. Here's the given the formula. That means G2 as defined above is called an extension of G, and it's called extension. And now Jamal start.
Great, thank you.
Okay.
Teacher, I have connection problems. It can be end.
No problem,
when I start
Jamal. Just start.
Okay. Let me talk about direct image of a set. Suppose if A in B is a function where A, D, F and R is included B. If E is included A, then we say the direct image of E under the function f is the subset of B such that if E is equal to fx and x is included E. You can see also in this picture.
Right.
Next slide, picture. Inverse image of a set. If f A is in B, is a function where H is included B, then the inverse image of H under the function f is defined to be set f minus 1h and x is included A fx, and A and fx is included H. Containing elements x is included A such that if x included H.
Right. And special types of function.
Special types of function. It is one-to-one, onto, and bijection. A function f from A to B is called one-to-one function, and a function f from A to B is called onto if for all B in B there is an A in A such that if A is equal to B. Also, it's called surjection.
If for two input there is just one output, this function is called surjection.
Yes. And bijection, the both of the onto and one-to-one is called bijection.
If for one input there are two outputs, then it's called bijection. And invertible functions.
Invertible. A function is invertible if on reversing the order of mapping we get the input as the new output. If other words, if a function f whose domain is the set A and image in set B is invertible if f power minus 1 has its domain in B and image in A. You can see also this equality and picture.
Let's talk about composite functions.
Composite functions. Suppose f is a function which maps A to B, and there is another function which function g which maps B to C. We map A can we map A to Z? The mapping of elements of A to C is the basic concept of composition of functions. When two functions combine in a way that the output of function becomes the input of other, the function is a composite function. Also, there's examples.
And it's enough. Thank you, Jamal. Thank you for your clearly representation. I think there is no unclear part. You really did great work, friends. Thank you.
Thank you, teacher.
And now it's iTouch's turn, yes? Only iTouch is remained. Is there anyone else? No, only iTouch. Great. Gumral, Allah verdi, talked.
Buna ihtiyac yoktu onda.
No. I think it's enough.
Müəlliməm prezentasiyam bu rəngdə deyil deyə.
Real analysis equivalent says iTouch Sultanova. It's not your presentation.
Mənim deyə, prostdakı rənglər dəyişilib, öz rəngləri qaçıb.
No problem, just talk.
Müəlliməm, bir də Nahid deyir ki, mən qəbul eləsin də mən də danışım.
I accepted Nahid. Okay, please start definition.
Okay, my Okay, bir dakika. Başka bir şey de açayım.
Mhm.
Okay, my today's topic is equivalent sets. Let's look definition of equivalent set. Let A and B be sets. We say that A is equivalent to B, or that A is equipotent with B, and we write A equivalent B if there exists a one-to-one onto function. The relation just defined is an equivalence relation. That's for every set A, we have A equivalent to A. If A and B are sets and A equivalent B, then B equivalent A. If A, B, C are sets, if A equivalent B and B equivalent C, then A equivalent to C. Let n denote the set of positive integers, it means natural numbers. We will write G0 to denote the empty set, and if n is in natural number, we will write this
Formal.
Yes. Okay. Okay. Next lemma. Let n and b be non-negative integers, then Gn equivalent Gm if and only if n equal to m. Next definition, a set A is finite if there exists n. Bu sen nece ters söyleyeyim bilmedim.
If set A is finite if there exists n from natural number set union just the element 0 such that A is equivalent to Gn.
Yeah, yes. We then say that n is the cardinality of A. If a set A is not finite, we're following this say is finite. We are still doing the simple things, but the following definition is very important. Like definition 3, a set A is said to be countable if it's A either finite or A equivalent to n. Let A be an infinite set, then I contains a subset B such that B equivalent to n. Let I be a countable set, and for every E
from I
let L be countable. Then is countable. Burada düsturu yazabilmedim PowerPoint'ta.
No problem. Just keep going. Definition 4.
Okay. Definition 4. Let A be sets. We'll write
okay. You can say less than or equal to B.
Okay. We'll write R less than or equal to B and say that A is smaller than B or has a smaller cardinality than B if there exists a one-to-one function if A equal to B.
And let's continue with just let me lemma 1.6 and finish your presentation.
Okay, let A and B sets. Assume B less than or equal to A and A is infinite. Then
A union B equal to A.
Okay. A union B intersection equivalent A, and if B isn't equal to 0, A and B
A cross B is equal to A. A cross B
cross B equivalent.
This is Cartesian product of A and B. Thank you, Aysel. Thank you, iTouch. Sorry. Yes, iTouch. Thank you so much. Despite the obstacles of online platform. Really, you did great work, guys. And finally, it's turn Nahid. Yes.
Yes, yes.
Okay. Okay, Nahid, your topic is the absolute value.
The absolute value.
Please start.
What's the absolute value? Every number and its opposite are the same distance from zero on the number line. Diğer tarafındaki definition. The other definition is the absolute value of a number is the distance between the number and zero on a number line. Bu manadaki yani
in English,
sıfır.
in English, just keep reading your presentation.
Okay. So that means a number and its opposite have the same absolute value. Because distances are always positive, the absolute value of a positive or negative number is always positive. For example, module 5 is equal to 5, and module minus 5 is equal to 5.
Great.
Because the distance from the 0 is 5. Yes, the absolute value of a real number A denoted by module A is defined by module A is equal to mod A if A is greater than 0. Module A is equal to 0 if A is equal to 0, or module A is equal to minus A if A
is negative number.
Negative number. Yes. Theorem 1. There are 4 theorems in that slide.
Okay.
First, model A product B is equal to model A product model B for all A, B are a real number. The second, model A square is equal to A square for all A from a real number. Third, if C is greater or equal to 0, then model A
less than
is less than or equal to 0. If and only if minus C is less than A is less than C. And minus model A is less than or equal to A, and it less than or equal to model A for all A from a real number.
And this is proof. You don't need to prove the theorem. Just keep going.
Okay. Triangle inequality are the theorem. If A B are from a real number, then model A plus B is less than or equal model A plus model B.
Great.
Proof'a ihtiyaç var mı Aldeğin?
No, you don't need to prove. Just keep going. The corollary.
Corollary, if A1, A2, and AN are any real numbers, then module in module A1 plus A2 plus AN is less than or equal to module A1 plus module A2 plus module AN. And there are some examples for the absolute value. First, determine the set A of x from a real number such that module 2x plus 3 is less than 7. solution, we see that x from A, if and only if minus 7 is less than 2x plus 3 and it less than 7. This satisfies if and only if minus 10 is less than 2x and it is less than 4.
And let's
dividing by 2, we conclude that A is equal to x from R minus 5 less than x and less than 2.
Yes.
And so on.
This is the end of your presentation. Yes. Thank you, Nahi. Yes. Thank you all, guys. Thank you for your work. I think at the end of this term, we will not be light-handed. We learned something from this term, despite the obstacles of online platform, despite you have very limited internet connection. And thank you for your attendance. Thank you for your tireless work. Really, I appreciate you. And we are powerful together, yes? And all of you guys got the greatest degree. And so this is the end of our presentations. Hope you will pass the final exam also successfully. Inshallah. Okay,
İnşallah.
guys. Bye bye. Yes.
Müəllim, final imtahanından qabaq da belə suallar atarsınız da biraz biz baxaq, işləyək, belə beynimiz işləsin. Olar?
Yaxşı, Artur.
Of course, of course.
Sağ olun müəllim.
Bye bye.
Bye bye.
Sağ olun müəllim.